Hi, this is Mrs. Doris. This is lesson 9-7 entitled Linear, Quadratic, and Exponential Models. Our objective in this lesson is that you will determine which model, linear, quadratic, or exponential, best represents a set of data. Alright, so let's look at linear. Linear functions are in the form of y equals mx plus b. Another form that you may see, that of course is the slope-intercept form, is ax plus by equals c. And that's the standard form of a linear equation. Just to graph one very quickly as a review, I'm going to take this equation, y equals 2x minus 3. All right, so what I see is that my y-intercept is negative 3. So on the graph at negative 3, I'm going to put my y-intercept. And then my slope is 2, or 2 over 1. Which means a rise of 2 and a run of 1, which would put it right here. Rise 2 more and run 1, and we can plot several more points for our graph. So this would be an example of a linear model. All right, notice that the change each time x goes up 1, y goes up 2. All right, for every one that we go over. All right, quadratic. A quadratic, which of course this is what we've been studying, is an equation in the form of y equals ax squared plus bx plus c. All right, and just by way of review, for graphing's sake, we're going to graph a very simple one, y equals x squared. This is our parent function. And the best way, of course, to do this is to simply make a little xy table. Okay? And we know that the vertex is at 0, 0. We know if we replace x with 1 and substitute 1 in for x in the equation, 1 squared would be 1. 2 squared would be 4. All right, so let's go ahead and graph those points, 1, 1, and 2, 4. And because we have an axis of symmetry in quadratic functions, we can also graph the same points. 1, 1 reflected across the y-axis would be the point negative 1, 1. And the point 2, 4 reflected across the y-axis would be negative 2, 4. So our function, our graph, appears something like this. All right, and then an exponential function is one that is of the form y equals a times b to the power of x. And this is one that can quickly grow off your graph. It can be either a decay model where it is decreasing exponentially, or it can be a growth model where it is increasing exponentially. So again, let's just take a very simple equation like y equals 2 squared, or excuse me, 2 to the x power. All right, and once again, I'm going to make a XY table to graph this. All right, if x is 0, 2 to the 0 power would be 1. Hopefully you remember that from our chapter on exponents. 2 to the first power would be 2. 2 to the second power would be 4. And past that, I'm going to be off my graph. So at 0, 1, I have a point. At 1, 2, I have a point. And at 2, 4. I have a point. Now we could actually put more points on here if I put some negative values. Let's put in like -1 for x. 2 to the -1 power would be 1/2. So at -1, 1/2, we would have a point. And what you see is a graph that's growing like this. It's going to get closer and closer on the left-hand side to the x-axis. And on the right-hand side, it's going to grow very quickly off the graph. All right. When the x values in a set of data pairs have a common difference, you can analyze data numerically to find the best model. When the y values have a common difference, use a linear model. When the y values have a common ratio, use an exponential model. When the y values have a common second difference, use a quadratic model. Now, the problem with this is when you're dealing with real-world data, seldom will you have an exact model. But you can determine which model best represents the data. All right, so problem 1, we're going to choose a model by graphing. Graph each set of points. Which model is most appropriate for each set? All right, well, I see, let's see, I just have one set of points that's negative. So I'm going to draw my x-axis down here, and I'm going to put my y-axis right here and label those. All right, so let's plot our points. We have 0, 0, 1, 1, -1, -5/10, and 2, 3. All right, here we go. All right, this is one that appears to be best modeled by an exponential. All right, we're not going to write the model for this. We'll get to that in a minute. All right, B. We have the points -2, 11, -1, 5, 0, 3, and 1, 5. So again, I see I'm going to put my x-axis right down here, and I'm going to put my y-axis right here. All right, let's plot these points. -2, 11. Would be right here. -1, 5. 0, 3. And 1, 5. All right, now this one, joining these points from left to right. It appears, even though it's not complete, that it's going to continue upward in this direction, and so a quadratic model would fit this data the best. All right, moving on to problem 2. Choosing a model using differences or ratios. Which type of function best models the ordered pairs? All right, well, first of all, I'm going to check to see if it's linear by taking the differences between my y values. I do notice that x is going up by 1 each time. All right, so 5/10, the difference between 5/10 and 1 would be 5/10. To get from 1 to 2, I would be adding 1. To get from 2 to 4, I'd be adding 2. And to get from 4 to 8, I would be adding 4. So it's not linear based upon this information. So while we're at it, let's go ahead and take a look and see if it would be quadratic. And to do that, we're going to take second differences. 5/10 to 1 would be adding 5/10. To get from 1 up to 2 would be adding 1, and from 2 to 4 would be adding 2. So since these are not the same, it's not quadratic. All right, so we can kind of guess right now that it, quadratic. Okay. We can probably guess that it is exponential, but let's prove that. All right, so I'm going to go back and look at my y values again, and I see I have an 8 and a 4. 8 divided by 4 is 2. All right, let's compare the next set. I have 4 and 2. Let's compare those. 4 divided by 2 is 2. Let's compare 2 and 1. 2 over 1 is equal to 2. And the last pair, 1 divided by 5/10, that's also equal to 2. So when we have a common ratio, we have a common ratio of 2, that shows us that this is an exponential model when there is a common ratio. Okay? All right. Problem 3, modeling real-world data. The table shows the annual income of a small theater company. Which type of function best models the data? Write an equation to model the data. All right, so with these numbers, we may want to get our calculator in hand. And so the first thing I'm going to do is I'm going to check the difference between each of these two numbers. So looks like the difference between these two would be 476. The difference between these two numbers, 19,215 minus 18,730 would be 485. The difference between these two numbers, 19,695 minus 19,215 would be 480. Okay, and the difference between our final ones, 20,175 and 19,695, and I'm just subtracting, I'm getting 480. All right, so I'm going to, we could take second differences. Second differences aren't going to be exactly the same, but here, between these big numbers, our common difference is very, very similar. In fact, we can just make the educated guess right now that it is going to best follow a linear model. It appears to be going up approximately 480 each year, but we could actually average that to make sure, but 480 is going to hit it pretty close. So let's write an equation. All right, so our income, which will be the y, is going to be equal to the rate of change, common rate of change is about 480 times x, all right, plus the starting amount. And so we'll use the starting amount in year 0, which would be 18,254. And again, this is an example where the real-world data doesn't fit this formula exactly, but it would be a good equation to use to predict what's going to happen to their income. All right. If you have any questions, please bring those to class, and I will see you here at Pershing. Thank you.